Thanks, Lloyd. Thanks for having me back up to this beautiful state. And I was actually in Florida before I came up, so it was a little bit of a different climate experience for me coming in yesterday. So a little different. Thank you, Mr. Chairman, members of the board, also for having me participate. I think we've had some really good discussions and topics that we've covered here so far as it relates to all of the things that Wyoming offers to solving the not only the energy questions that we have in Wyoming, but the energy questions that we have as a country and the energy problems that face the globe. As Governor Meade alluded to, there's a huge need to address the how we're going to supply and meet the global energy needs of the future, and that all has to sort of take into account, I think, a convergence of a multitude of stakeholders that are involved, whether they be government officials, politicians, regulators, environmental groups, ratepayers, investors, and financial markets. And coming up with a solution, a one-stop shop sort of thing, is probably not very realistic, but certainly an amalgamation of solutions is probably much more the likely outcome. So all of that being said, I think it's important, sort of coming from a high level, drilling down. Sargas has, I guess, over the last 11 years, and I've been involved for about 2 of those 11 years, focused on several themes when it's tackling this approach to how to provide a competitive, cost-competitive choice to utilize fossil fuels to meet this energy challenge for the several decades to come. It was founded in 2003, and effectively it was a sort of hived-off group that used to run ABB Carbon's platform. They worked a lot with pressurized boiler systems in Europe, and fairly sort of fluent in these sort of pressure vessel, pressurized combustion process engineering, mass flow backgrounds. This group of gentlemen ended up in 2003 coming together to come up with a solution to address the concern, which was in Europe at the time rather, a concern over how do we use coal in a carbon neutral or low carbon format. They developed a technology called the Sargas 275B, which is effectively comes in trains of 90 megawatt equivalent units, which is effectively a pressurized boiler process with a compressor, and I have some process flow slides we'll walk through, that effectively utilizes coal and compressed air in a pressurized boiler format and runs the post-combustion gas through a hot potassium carbonate process, again under pressure. The benefits of this pressurized process effectively have proven themselves in the form of reduced capital investment up front, because you're using a lot less steel, a lot less plant layout and footprint to basically run the same amount of volume throughput through the system as you would with the atmospheric unit. So key to the Sargas technology platform is its pressurized use of its boilers and compressors. The other technology that came about perhaps most recently in this company's history in 2011, they started down the track of developing a solution for natural gas. They did that in conjunction with General Electric. General Electric obviously has a very substantial interest in the gas turbine development business. In this case, the Sargas guys ended up using a GE LMS 100, which is an aeroderivative gas turbine that GE offers. GE has agreed under our agreement to modify the turbine at their own expense to basically go ahead and strip out the combustion gas after the second stage, which will, again, I'll walk through in a more detailed schematic. We've been currently focused on deploying this gas technology in Texas. We think Texas has a long history of EOR. It's got a long history, and obviously the natural gas is a very prolific feedstock for a lot of the generation in Texas. So we're currently working on a project in Point Comfort, which is just north of Corpus Christi along the coast, and there's a lot of opportunities within the EOR space there that would utilize the CO2 from the project. So we're working from both the producer side of this, at the oil producer level, the sort of engineering side and the manufacturing side with GE and others, as well as just a general selling. The electricity market in Texas is liquid. You can sell into the market. You can hedge your commodity if you want to. So there's a lot of flexibility there in developing and permitting and constructing a unit. In the past and up to current, we've executed various agreements with various sort of global energy industry stakeholders on the manufacturing and OEM side, including GE, as well as a Korean company called Daewoo Shipbuilding Marine Engineering. Daewoo effectively paid Sargas to create a couple of feed studies for both the coal and the natural gas technology, of which it did go ahead and put on barge-mounted vessels that it could potentially ship globally from its shipyards in Korea. Again, the thought here was to try to develop a product starting from what the commercial side of the equation wants and working backwards from there. And so we'll go through a little bit more detail on how we do that. So this is the gas-fired technology process. It's 250 nominal megawatts. There's about 14 megawatts of parasitic load. Half of those megawatts are associated with the actual CO2 capture process. But effectively, if I can get this light to work, you start with this modified big air compressor, which in this case is the GE LMS 100. And from that unit, the third stage has been removed, and we'll just put it over here for now, which is basically the expander or power turbine piece. And we take the post-combustion gas stream, run it through a heat exchanger, and then we actually refire that gas in what they call a pressure vessel, or basically it's a pressurized HRSG. In that pressurized HRSG, you're going to increase the temperature of the gas. That gas is in the HRSG at about 7 bar, and effectively you're running a steam process through the HRSG as well, where you generate the majority of your power in a steam turbine. From that HRSG, the post-combustion gas, if I can get this to work, is going to actually go through a series of cleaning for NOx and carbon monoxide, etc., run through another set of heat exchangers, and then it's going to run through this hot potassium carbonate process. The hot potassium carbonate process is a bit different than amine, as we've alluded to in previous discussions. Amines is a much more energy-intensive process requiring, it's very good at actually capturing CO2 off separating it from various compounds and molecules. But the problem with it is that when it's coming to removing the CO2 from the amine compounds, it's quite energy intensive. You've got to apply a lot more heat energy to remove the CO2. So in hot potassium carbonate, it's actually much simpler, but the trick is it has to be an under pressure. So basically it's baking soda in a more sort of juiced up format that we run this through an absorber and then a desorber, where the effective combined potassium carbonate with the CO2 is effectively depressurized, and that naturally or physically rather separates the CO2 back out from the potassium carbonate. The other benefits of this versus amines are that the potassium carbonate solvent doesn't have nearly as high a degradation factor over time as you see in most amine-based systems, where you're constantly having to ship in tons of the product to actually replace the solvent. Frankly, and I have another slide of this, just the actual environmental hazards dealing with amines. Amines can be create some pretty nasty byproducts. I'll go through some of that. So this ultimately creates industrial salts and water vapor. If you remember, we put the power turbine or the expander turbine back over here. The remaining sort of content of that now sort of post-combustion gas, and I refer to that because the flue gas actually comes out of the expander. That post-combustion gas then is run through the gas expander, runs a slight gas turbine power component, and then goes back up the stack. Just like some of the other presentations, the actual sort of flue gas content, when you're looking at it based on EPA, BACT regulations, it's well below the BACT requirements for existing natural gas-fired generation today. We also, like I mentioned, have a coal-based solution. The coal-based solution is actually, in fact, pretty straightforward. The actual back end is the exact same hot potassium carbonate process as you saw in the slide before that, except on the front end now we've added basically a pressurized bubbling bed boiler process. So the difference between just the atmospheric combustion process that you would see in the boilers is that we actually take air and we blow it into this combustion chamber, which is pressurized to achieve a nice pressure, which is about 7 to 8 bar. In that system, we're actually blowing in sort of a dolomite, cold dolomite paste slurry, if you will, and actually combusting it and making a nice temperature in that boiler and effectively pressurizing that post-combustion stream, which is then again fed through that hot potassium carbonate process, which reacts really nicely with pressurized post-combustion gas. In this process as well, again, the compressor effectively balances itself. You get a net actual 2 megawatts. And then the net off the back end of the steam process is actually about 88 megawatts of power. This process can be scaled basically by simply adding either larger compressor, more compressors, or and stacking the pressurized boilers alongside one another. And I'll go into some of the applications of that in a second. Again, these are all the nasties that end up sort of getting kicked out of the back end of an amine process. All sorts of nasty carcinogenic, mutagenic sort of compounds that are really, you have to have heavy permits and careful handling to dispose of. When you compare that to the hot potassium carbonate process, it's, basically salts and water vapor coming out of that. So what we've tried to kind of do, again, coming back from the commercial side and working backwards a little bit, is we've really tried to develop a product that meets one of the, I think, challenges that, frankly, the CCS industry has failed to address in the past, which is how can I sell a cost-competitive electron that doesn't overburden governments, ratepayers, politicians, etc. If you think of basically kind of, again, this is some analysis that we've received from Bloomberg New Energy Finance and an investment bank. We've looked at this and kind of tried to stack our technology. This is all unsubsidized, so no PTCs or ITCs or any of that sort of tax subsidy going on. We think that our units compare very specifically with their traditional energy alternatives. We have a complete power package, power system, or power island maybe is the way to think of it. So again, this is going to be suitable for refiring and greenfield applications only. And basically when you look at us next to the alternatives, again, I think without any association for any value of our CO2, we're about $10 to $15 a megawatt hour, 1 to 1.5 cents a kilowatt hour more expensive than the alternate traditional form of energy without carbon capture. So again, simplified business model here. What we do is we're effectively taking various forms of feedstock, coal or coal co-fired with biomass or natural gas, running it through our pressurized process, and we generate what I call EOR-ready CO2. I'll go into that in a second, and I'll call power that PSCs and PUCs don't necessarily puke all over, that we're raising rates exorbitantly to potentially do. The actual quality of the EOR grade CO2 coming out of the back end, again, it's EOR ready, meaning we have very low oxygen content, very low moisture content in the CO2. It's actually coming out at about 150 psi, so the energy requirements necessary to step it up to injection ready quality, which typically, depending on the geology and the pipe system that's going to carry it to the field, could be 1,1500 psi. At least those are some of the cases we're working on in Texas. It's about 10 megawatts. Compare that to some of the projects on the market today. Actually, one project that's in construction, I think they had to buy a 70 megawatt 70A gas turbine just to feed their parasitic loads from the CO2 capture system, as well as for their compressor systems that they're installing on site. So we're much more efficient than that. What does it mean for producers? Well, again, and somehow I guess the numbers here got sort of screwed up, but effectively if you start with $4 MMBtu natural gas as an input, and you actually end up getting some cost assigned to your investors at the power plant, plus your cost to operate the facility, but you're getting a credit back for the fuel and the power that you sell, basically the market price of electricity. You end up with this sort of CO2 value. CO2 value, I think, is anywhere, depending on what the market price is willing to pay for it. I think there's probably a fair argument to say that producers are willing to pay anywhere from, for a man-made CO2, $20 to $40 a ton, thereabouts. Again, targeting that sort of price. And then you factor in what a typical cost structure might look like on an EOR project. Just at $50 a barrel, we're just break even for CO2 EOR producers. And again, as you start to think about where the price of WTI might go, producers benefit quite substantially from our CO2. And Lloyd, I'd like to submit an updated slide where the numbers are correct on the axis here. So for owners of one of our systems, again, if you compare it to what the market has today in combined cycle technology, Certainly, combined cycle with electricity only is going to be more profitable than our Stargate 250 unit. It's more efficient. It's got a lower capital cost intensity because it doesn't have the back-end capture system on it. However, when you factor in the potential, again, somewhere around $20 to $40 worth of CO2, that upside potential can be quite substantial. So asset generation owners that can monetize the CO2 actually have much greater profitability opportunities than just traditional combined cycle power plant owners. Some overviews about where we are in Texas on our launch project. Again, Point Comfort, just sort of northeast of Corpus, or between Corpus and Houston. It's a 250 megawatt gross facility. We've entered into interconnect negotiations for the interconnect agreement. We've worked with an oil producer nearby to sell all of the 100% of the CO2 output of the facility to them. The site work is actually a brownfield site. There was an existing power plant located on the site, so the actual permitting and environmental work, also given the fact it's Texas, has been a bit of a quick process for us. We're pretty much ready to go there. We've got all of our water. We actually have the ability to do once-through cooling if we wanted to. And effectively, the EOR company will purchase some of our load because they have a lot of on-site compressor usage that they use on their CO2 recapture units. And we will sell the rest of the electricity to the market. On the two kind of bottom rungs, it's interesting. One of the things that a lot of the market has told us is that we're not going to be the first in kind to actually use a non-commercial technology. We demonstrated our coal unit both in Stockholm and at the Console test facility outside of Pittsburgh, Pennsylvania. We demonstrated 98% carbon capture efficiency on that unit in Stockholm. We've not demonstrated the gas unit. We will actually go to commercial full-scale deployment of the gas unit right away in conjunction with GE. And again, the trick is on the EPC side, what our customers have said is they want to wrap. So we're actually working with a couple of EPC counterparties at the moment that are willing to entertain the idea of wrapping the entire technology package for us. Because again, it's an amalgamation of commercially proven equipment, GE LMS 100, standard pressurized HRSGs, basically a bin-field CO2 capture process, hot potassium carbonate, and a steam turbine process. They're willing to sort of wrap the entire technology and take that risk on a performance basis. On the financing side, at the end of last year, I'm sure many of you guys saw, there was a DOE solicitation that came about for fossil fuels. Advanced Clean Energy was the title of solicitation. It's a loan guarantee program. It actually we actually went ahead at the beginning of this year and applied for it with traditionally, or up until that point, we had been very adverse to looking at any government solutions for financing this opportunity. We were actually being heavily contacted and engaged by some of the federal regulators that really wanted to see a higher degree of involvement. So we ended up going ahead and moving forward with this. We're moving forward in that process with the DOE actually as we speak. So we hope to sort of keep moving on that as long as that train may take. So it may take quite a while, but we'll see. Some of the opportunities to use our equipment in refiring applications, both for whether it's a coal to gas switch, whether it's a coal to coal switch. On the actual sort of gas side, one of the important things that we think is probably pretty crucial for today, given the fact that a lot of IOUs and municipalities probably don't need or want to have to deal with a lot of additional power onto their systems. Our units, because of the pressure that comes out of the back end of the LMS unit, we can actually take a lot of the existing steam turbines that are used today and a lot of the coal-fired applications around the United States, and actually go ahead and swap out those boiler units, reuse those existing steam turbines, again, because we supply enough high-pressure steam with one of our LMS units, or actually in this case, let's say it would be two of our LMS units, and they would actually create less incremental megawatts going onto the grid versus a traditional refiring with like a frame unit. So we think that's very profound for a lot of utilities thinking about doing fuel switching, etc. today. The other opportunity with the gas unit, it allows for some flexibility. We have the ability to turn the gas unit down by about 50%, which again, we think is pretty profound for optimization and flexibility purposes. We realize that the load profile in today's world is a lot different than it used to be a decade ago, and in today's world you need more flexible generation to sort of follow the sort of load profiles a bit better. You don't need to run these units all out, although we would love for you to run the unit all out because you make more CO2 for EOR and oil. On the coal side, etc., the coal side looks like basically if you take an atmospheric unit and you look at the sort of square footage or sort of volume that a unit like this would require versus our unit, because again we're doing everything under pressure, it actually fits quite nicely with a lot of existing boilers and a lot of existing coal-fired power plants. There's no real additional site expansion or layout required other than simply for the initial sort of swapping out of the boilers and potentially some laydown area. There's compact design that allows for this implementation with most existing plant footprints. And again, we would be, if we had a 180 megawatt steam turbine, we would stack 2 of our boiler units to run, and in front of that, as well as you may have 1 large or maybe 2 smaller compressors to go alongside that. So we think it could be a very good, flexible implementation program for existing coal-fired generation. So, as I said kind of earlier on in the presentation, I think that a lot of the CCS initiatives globally, and Europe has tried to incentivize CCS, but it's failed. And it's failed for lots of reasons, but I think one of the primary reasons is that, again, there haven't been any real technological developments that have really addressed the issues of cost. And I think we're just starting now to see a lot of technologies that start to address that issue. The U.S. hasn't really embraced the carbon market, and I should have put RGGI, I guess, next to California, because I guess it is an offset or a carbon-like market. But really, outside of AB 32 in California, the U.S. hasn't really come out with a carbon market. As we've talked today a lot about the EPA, the EPA is trying to mandate and regulate carbon under how much authority, I guess, the president is willing to give it. But again, there's a lot of uncertainty there. So this technology that we're looking at and that we're developing and working on, and that we're frankly ready to go and start commercial efforts on, I think addresses a lot of the challenges that these market paradigms are sort of gradually shifting toward, and allowing us to continue to use a lot of our fossil energy. The other challenge that we face today is electricity demand. It really fell apart after 2008, and frankly in OECD countries it hasn't really come back. That coupled with demand response programs, I think as Al mentioned in one of his earlier discussions, demand response has actually been, whether you can measure it or not, has eaten away at demand and been somewhat successful in most states, I'd argue. So you actually haven't had much net increase in demand growth, or real demand growth for electricity. So that obviously causes a lot of heartache when you start making decisions about adding new generation to the grid and you're not really having the customer base to do that. Again, if you can swap out existing units with more sort of carbon neutral, but also getting value from carbon, we actually think that's a great opportunity, and it's certainly a mitigant to the future risk or uncertainty of regulated carbon markets. Again, third point, CO2, I think, has a lot of benefits. EOR, I mentioned, is what we're focused on largely because it's a proven commercialized marketplace. Dawn and I had a great chat last night. I think there are lots of great other uses of CO2 that are out there that hopefully we'll continue to work on. But again, I think that the large-scale use of CO2 right now, we don't just want to stick it down into a line formation or take it into the North Sea and stick it there forever. I think we want to get some additional hydrocarbons like oil out of the ground with it. So the problem with that is that you have to have infrastructure to take the CO2 and move it places. So we think that the right opportunities for this technology are ultimately going to require participation from governments, private enterprises, and again, any sort of financial market participants that are going to be able to support and see the big picture here. Wyoming, I think, has a lot of the right makeup to do this. I think that, in the state of Wyoming, obviously, there's a big history with CCS, or actually EOR, using man-made CO2 for that matter to derive EOR. I think that there are lots of great opportunities to utilize existing rate-based assets to feature some of this technology and lead some of the initiatives here. I think the entities like the Wyoming Pipeline Authority and other infrastructure entities like the WIA can actually help stimulate the development of some of the logistical infrastructure required, both on the transmission and the pipeline systems. And I also think that, you know, there's a story for growth here. You know, there's a story for both the growth, for example, in the severance taxes with increased EOR production, and there's frankly just an overall economic stimulus that occurs, I think, when you take cost-competitive technologies and you actually start to do things with them that are more sort of creative and forward-thinking, and able to drive that value in the market. So I think Wyoming has all the right mixture of that. It's just a function of how we can sort of put our heads together and drive that innovation together. So with that, I think I'm done with this presentation. Open for questions, of course.
Questions from the board? No questions from the board. Question from the audience? Coming at you.
James Goodrich, Goodrich Land Research. I do a lot of land work for oil, gas, and mining. And here in the Rocky Mountain region, we have a lot of very small oil fields and smaller grids than what you may find in coastal Texas. And I'm wondering how your processes, how do they scale down? Is it possible to scale it down to the 20 to 40, 80 megawatt range?
And actually, both the coal units, so the smallest we sort of scale to on the coal side is 90 megawatts. On the gas side, actually, we could use, for example, GE makes some smaller aeroderivative turbines, the LM6000, for example, that we could use that would, I think, provide about 50 megawatts of power, and similar kind of CO2, although scaled down much more substantially. The interesting trade-off is as you reduce the sort of scale of your input, your output also proportionately declines. And so for a lot of the EOR producers in the world, they would love to have millions of tons a year of CO2 to inject for enhanced oil recovery. So it's always a balancing of that trade-off that we've kind of had to juggle, frankly, James, while we're trying to commercialize the product. So we think, you know, these are kind of the right size units. Obviously, there's a lot of ability to scale them up, not as much ability to scale them down.
Hi, Roy Sensenate with AMEC. Have you done any comparisons with IGCC technology? It seems like some of the projects are really going way over budget these days. And how does your technology compare with that on a dollar per kW, let's say, capital cost?
Yeah, so I can speak very specifically about the gas technology because I've been pretty involved in the EPC discussions on that basis. On the coal technology, I have not been as close to the EPC discussions, but I think you're right, Roy, in that I think that it is, in its sort of general makeup, probably to some, it's not going to be the cost of a supercrit unit on a dollar per kilowatt basis, but it's not going to be the cost of an IGCC unit on a dollar per kilowatt basis. So we would probably target some kind of a range in between those two. On the gas side, though, specifically what we've looked at, if you look at combined cycle units today and sort of where the EPC sort of sale point is coming out at, because we have the CO2 capture system, because we have some, you know, higher grade metals, higher grade steels in some of the piping, more piping, etc. It's a bit more process orientated. We're probably about 20% north of that EPC price, and we feel pretty comfortable with that sort of estimate right now.
Other questions? So let's give Chris a hand, please.